All right, so this is going to be a lecture on the scientific method, and I'm presuming that you've gone through the pages in the textbook. Talk about the example of the flashlight with a burned out bulb. And first you think that there's a problem with the batteries, but then when you change the batteries, the flashlight still doesn't work, so you go with hypothesis 2, that the bulb is dead. Yeah, I know this is just common sense. It doesn't sound like science. But the point of making that example is that in a scientific experiment, we apply the same type of common sense, but in maybe a more rigorous, blown out way that ultimately offers us a better opportunity to either generate strong supporting evidence for a hypothesis or not. Okay? It's always possible that the outcome of your experiment could show that your hypothesis is probably wrong. Okay? And you've also seen the earlier video on Cuvier and the contrast between catastrophism, which was the explanation that canyons and mountains occurred as a result of this gigantic flood. And we said that this was a non-scientific hypothesis because it could not be validated. If something's the result of the hand of God, you really can't reproduce that in any kind of experiment or observation made on natural systems. The Hutton/Lyell model of uniformitarianism is completely scientific, and this has nothing to do with the fact that one is right or the other one is wrong. It could be the other way around. I mean, you have many scientific models that are completely wrong. The reason why uniformitarianism is scientific is because it can be validated or not by observations from the natural world. And it's really important to understand that science only deals with those phenomena that are explainable by the natural laws of the universe. And this is why you'll never see any discussion of creationism or creation in a legitimate science class. Okay. So let's turn our attention to the example of the deer mice. So you've got Hickstra's field study on deer mice, genus Peromyscus, and the coloration that you have in different environments. So you've got this beach population where the coats are light, and hey, it just happens that the sand, the substrate of sand on this light colored beach is a pretty good match for the color of the coat that we have in these deer mice. And it's the same species over here, only in the inland population where you're looking at a darker field, the mice are darker. And you say, yeah, that's really great. That's obviously a situation where camouflage is helping the mice survive. And so we want to validate that hypothesis with an experiment. And the experiment that we're presented with is actually pretty nice. But what I want to do is I want to consider what it is about the way this experiment was set up that made it nice as opposed to being flawed. Okay? And there are three things that I'd like to draw your attention to here. One is controls, and then you got replication, and the third one that I want to talk about is the honest reporting of results. Okay? So for a control experiment, you really need to have some sort of baseline level that you could compare things with. For example, somebody that wasn't so scientifically inclined might have set up an experiment where they put a whole bunch of dark-colored mouse models out here on the beach and a whole bunch of light-colored mouse models over here, and you just sat back with binoculars and said, hey, I'm watching all these mice get slammed by the predators. The hawks are coming down and really hitting those dark mouse models hard over here, and they're slamming the light-colored mouse models over here. And so I guess the question is, well, what did Hickstra do that was different? I mean, what if? What if she just put out the dark models on the beach and the light models in the field? And then she went on to report that indeed these models were severely attacked by predators. Okay? And of course, Hickstra didn't do this. But if she had, and then she were presenting these results at a meeting, and you were in the audience, you might even be the one to raise your hand to point out that this experiment is totally bogus because of a lack of controls. Okay? How do you know that the non-camouflage models are really being hit hard unless you know what the attack rate is going to be on the camouflaged models? The obvious thing to do is exactly what Hickstra did, which is to put out an equal number of non-camouflage models to serve as a baseline reading. And so you could compare the attack rate on the non-camouflage models versus the ones that are camouflaged, and there should be a difference. Okay? Having only attacks on the non-camouflage models is not going to give you any real valid information. Okay? And so that's, I think, pretty straightforward and obvious. Okay? So let's go back to this, and I want to give you a slightly more difficult version of that same question of how controls may be important. And so let's do another what-if scenario. What if we didn't have the beach population at all? What if we only put out maybe an equal number of light models and dark models in this inland population, and then we proceeded to observe the fact that in this inland habitat, the dark models didn't get hit so hard, but the light models got hit pretty hard. In other words, we ended up with the same results. Okay? So what if? I want you to think about this for a little bit. You might want to pause the video here and think about, well, what could have been the problem here? I mean, how could this result might have happened even if there was no necessary bias against the non-camouflaged mice? Okay. So now again, this one is quite a bit harder, okay? And it does provide a controlled experiment because we have the light models and the dark models to compare, and in that respect it's good. Okay. Now thinking about things a little more critically, you might argue, I mean, this is just kind of like a total devil's advocate sort of thing, but you might argue that these mice were painted different colors, right? What if there was something in that light paint, the paint they used to make the non-camouflage models, that was really attractive to predators? Maybe there was some kind of smell that comes out of the light paint that it brings on attacks by hawks and foxes, right? Or maybe there was something completely repellent in the dark paint. There was some kind of chemical signal coming off the dark paint that was causing them to be not just use like a predator stay away sort of signal. Okay? In other words, maybe it was all about the chemistry of the paint that was used, and it had nothing to do with what the predators were seeing. Okay? Now, if you go back to Huxter's experiment, she didn't really do that. She actually had a kind of like a vice versa situation, right? So in addition to having the light and dark mice over here and seeing the light mice get slammed in the inland population, she also had the light and dark mice in the beach population, and she watched a higher rate of attacks occur on the non-camouflage population even there. And so the way that her experiment was set up, it was kind of like you had a built-in control against that criticism that we raised. Okay, it would be far less likely for it to be a chemically induced difference in attack rates because we actually saw the opposite results against a different background. All right, let's talk a little bit about replication, okay, because this is another important feature of scientific experiments. We'll be seeing this in some of our experiments. We don't do experiments just once. We like to do them at least twice. The more times we do them, the better. Okay? So let's do another what-if situation. So the way it's described in the textbook, Huxter and her students put out a huge number of these mice in the two different habitats. But what if, instead of putting out a large number, she'd only put out a few, maybe 10 light mice and 10 dark mice in each habitat? And then she found that in the entire beach experiment, she had one camouflage mouse that was attacked and 3 camouflage mice that were attacked. Three non-camouflage mice that were attacked. So on the beach, you would have 3 dark mice getting slammed, 1 light mouse getting slammed. And in the field situation, she would have 1 dark mouse mimic getting hit and 3 light fake mice getting attacked. Okay? And so these would actually be the same percentages relative to what she actually reported. Roughly 75% of all the attacks were on non-camouflage mice. Now, if you think about this just a little bit harder, okay, consider the possibility that there was absolutely no difference in the way predators saw the 2 mice. The attack rates really are about the same in both habitats on the light and dark mice. Okay? But we're only talking about 4 attacks, right? And so in other words, each time a hawk hits one of these fake mice, it's kind of like a flip of a coin. Heads, I attack a dark one. Tails, I attack a light one. And if you flip a coin 4 times, getting 3 heads and 1 tail is not that weird of a result, right? It's not that unlikely. In other words, without a much larger experiment, having 75% of the attacks occur on non-camouflaged mice would not be very convincing at all. Right? Now, if you flipped a coin 400 times and you saw tails resulting 300 times, that would be pretty weird. Okay? And so the bigger the experiment, if we actually got 300 out of 400 attacks occurring on the non-camouflaged mice, that would actually say something a lot more strongly about our hypothesis. It would actually give us much, much stronger support for our hypothesis, which is that mice do better if they blend in with their background. Okay. Now, in Hikstra's experiment, if you look at the numbers, she only has 7 total attacks in the beach environment and 21 total attacks in the field. And yeah, it's 5 out of 7 in the beach were non-camouflaged and 16 out of 21 in the field were non-camouflaged. And those really aren't terribly convincing numbers. They're not adequate as far as I'm concerned. And that's because of my experiences at having seen large numbers of experiments. And so I guess the question at that point becomes, well, how do you tell if a sample for result is large enough? How large does a sample have to be before the results are going to be meaningful and compelling? Well, that's where statistics are used, right? There's a whole side discipline of statistical analyses of results, and we're not going to get into that here. That's more discussion than you need to have in a BIO100 class. What I do want you to be able to see here is that a result based on 1 out of 4 or 3 out of 4 is far less convincing than a result where you've got 300 times out of 400 times the non-camouflaged mice got attacked. Okay. I think that's pretty accessible. Right. Now, there's one more thing that I think is really timely. It's apropos to some recent discussions that are going on in science right now, which is when it comes to reporting the results. Okay, so obviously, if you lie about the results, maybe there weren't any differences, and Hoekstra said there were differences in the attack rate between camo versus non-camo. Let's presume that's not the case. But even if you report all the results perfectly, it's possible for there to be some underlying dishonesty. And I'm not saying this is actually true of Hoekstra, but here's another what-if scenario. Okay. So I'll talk you through this. Now, maybe in reality, Hoekstra and her students did the same experiment. They put out light and dark mice in the beach and in the field and in the desert and in the mountains and in the middle of a pond. And what if they set up 25 different study sites and they got results that varied? Sometimes the non-camouflage were attacked more, sometimes the camouflage were attacked more, sometimes the attack rates were equal. But what if she had just cherry-picked these 2 results of the beach and the field to report? Okay. Now, you can't say that she didn't report her results accurately in the beach and the field, because those were actually the results that occurring as they actually occurred. But if you cherry pick your results, if you selectively report on only those results that support your hypothesis, that's not so meaningful. I mean, if you were to set up 25 completely random experiments and look at the results across that entire set of 25, the chances are actually pretty good that you'll have 2 of those results, 2 of those 25 experiments, showing you a significant difference between camouflaged and non-camouflaged. Okay, it might be a big difference in field A and in beach 16, right? Now, there's really nothing behind the attack rates in camouflage versus non-camouflaged, right? I mean, we said that. It just happens that in 25 studies, you're going to get a result that gives you a difference every once in a while. And if you only report those two results, that's dishonest. You're making it sound like there's a real significant difference between camouflaged and non-camouflaged, when the truth is that there really is no difference. Okay? This is a legitimate problem. This is something that does sometimes occur in real scientific studies, and one of the things that we need to clean up are experimenters' behaviors and the recognition that this particular practice, it's called p-hacking, where you only select the results that kind of support your hypothesis. It's basically cherry picking, and our safeguards against this type of scientific dishonesty is really there are really two levels of policing. The first one is peer review. So when you submit a paper for publication, you submit your results in a paper for publication, your paper is going to be scrutinized by scientists who are familiar with the situation well enough to be able to detect any irregularities that might suggest this type of dishonesty. Okay? The other ultimate safeguard is reproducibility, okay? Because scientific results, in order for them to be actually significant and meaningful, they have to be reproducible. Okay? So somebody else should be able to come along and do exactly what you say you're doing according to your report, and similar results should be obtained. Okay? Now, obviously, if there are any kind of selective reporting or academic dishonesty, you would be replicating the experiment, you'd be reproducing the experiment, but not getting the same results. Scientific results are, by their nature, necessarily reproducible. And so those are my three major considerations that I want to pass along to you. Controls, good controls for your experiment. Replication, the size of your experiment is really meaningful. And honest reporting of the results. And so now I want to give you guys a chance to test your ability to critique scientific experiments. And so I've created this virtual experiment, which I'm describing something to you, and you decide what's wrong with this experiment. Okay, so here we go. Let's say we're doing a test to see which kind of bait is more effective at catching fish. Okay, so your hypothesis might be crickets are a more effective fishing bait than worms, and so I'll set up an experiment. I've got 2 ponds. I'll put 10 people fishing with crickets in one pond and 10 people fishing with worms in a different pond, and as a result of doing this experiment, the people using crickets caught 3 times as many fish as the people using worms, and I might conclude that my hypothesis has support. Crickets are definitely more effective as fishing bait than worms. So you might want to pause the video here and decide, well, is this a good experiment? Are you totally convinced? What are there any flaws? Well, what would the flaws be? Okay, so I'm hoping that you're, if you're thinking about this, remember I've got the cricket people in pond A and the worm people in pond B. And maybe the cricket pond A, just had more fish, or maybe they were more active there because the water was warmer. The people that were fishing with worms didn't have good conditions, and so if you were to switch those 2 ponds, you might actually see the worm fishermen do better because they're fishing in the better pond. Okay? So maybe as a remedy for this criticism, you'd want to have all 20 of the people fishing in the same pond using either crickets or worms. That might be one way of getting around this criticism. Okay, the issue here is really one of controls, right? And so the 20 fishermen, the 10 fishermen that are fishing in pond A with crickets, we don't know how well they would be doing if they're fishing with worms. So we put 20 people there with 10 people there with worms, and so we actually have a way of comparing. So designing a scientific experiment is kind of like an art form. Okay? You need to balance all of the constraints and considerations. You want to maximize your ability to detect a result that would be predicted if your hypothesis is true, as well as a result that would show you that your hypothesis is wrong. Okay? If it's impossible for your experiment to actually detect a result that's meaningful, then there's really no point for you to even do your experiment. Okay. Let's do another worms or cricket experiment. Okay, so this is the same hypothesis. Crickets are a more effective fishing bait than worms. And so what I do is I put out, I'm the only fisherman here, so I put my line out with 2 hooks. One is baited with a worm, and the other one is baited with a cricket. And I do this all day long. And I end up catching 3 times as many fish on worms than on crickets. And so I conclude that my hypothesis is incorrect. Crickets are not a more effective fishing bait than worms. Okay, so I'll pause it here, and you tell me what's wrong with this experiment. You probably should have come up with the idea of replication. Okay? So if it's only me, that's not a very good sample size. Maybe I caught 1 fish on crickets and 3 fish on worms, and that would be completely meaningless. I mean, I don't think one isolated result is going to tell you much of anything. So I guess maybe ideally you would have multiple people fishing with worms and crickets at the same time. And maybe even if it were valid that we had multiple people fishing, it might be limited to this one pond, or maybe it might be limited to the day on which we fish. Maybe it's a rainy day, and so there are lots of worms around, but few crickets, so the fish are going for worms. Okay. I don't know, just making this up as I go along. Or maybe it's not meaningful for a different reason. Maybe people never fish with more than 1 hook. And so if you were to fish with 1 hook at a time, crickets are great. Crickets work way better than worms. But if you fish them both together, the worm maybe drags down the cricket dies, and it's not moving anymore, so the fish will just go for the worm. Okay? But basically, these are all points that demonstrate the potential flaws in this experiment, and pointing out some ways in which, even though you might get a particular result, it might not offer complete or convincing support for the hypothesis. It's not proving anything. And again, we come back to the idea that we don't ever prove a scientific hypothesis. We just offer support for it, because there's always a better experiment that could be done. There's always a potential flaw in the way the experiment was run that would actually cause you to come up with the wrong conclusion. So your objectives at this point, what you should be able to come away with this video with, is an ability to, 1, understand the importance of these 3 things we talked about: adequate and appropriate controls, replication, and what we mean by honesty of reporting of results. Okay. The second thing I think that's kind of neat for us to be able to do at this point is to use our developing understanding of the scientific method to critique a proposed experimental design for some of the basic flaws. And so at some point in the future, you should probably anticipate my coming at you with a question, maybe on a test. Got your attention there, huh? So maybe this test question will be describing a scientific experiment, and it'll be your job to critique it and identify what the flaws are with this scientific experiment. All right? So that's it for this video.